Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the second lecture of this week. By now we know how to construct shape function for quadrilateral elements, and we had a detailed discussion on that. But as far as triangular element is concerned, we know only how to construct shape function for a linear triangle, 3-node triangle. Now today and next week our topic of discussion is how to construct shape function for higher order triangular elements. So let us start. So if you recall, this is the Lagrange simplexes, and this gives you what are the terms to be considered for a particular element. For instance, if we want to construct shape function for a 3-node triangle, then in the approximation we have to take these three terms, right? So our approximation for this will be fxy. This will be C1 plus C2x plus C3y. So it is a complete linear polynomial. Similarly, if we have to construct the shape function for a 6-node triangle, then the monomials that have to be taken in the approximation is all these three, all this. So in this case, our approximation should be, our starting approximation should be fx is equal to C1 plus C2x plus C3y plus C4 x square plus C5 xy and then C6 y to the power y square. So this is a complete quadratic approximation. Similarly, for this element we have to take all these terms as well. So this gives you, this is a guideline when you start with an approximation and what are the terms you have to take in the approximation. And we know that completeness is important. So in the approximation, we need to, any order of approximation we are taking, we have to take all the terms lower than, including and the lower than that order, then only our approximation will be complete. And the completeness is an important, completeness is very important in convergence. Okay. Now, so what is the approach we followed while constructing? We know how to construct shape function for this. And what is the approach we followed? If you recall, now we have this approximation, and then this approximation is satisfied at every node. So that is the imposition of the interpolation property. So at whatever the nodal values, our approximation must interpolate that values, and if we impose the interpolation condition, it will give us a required number of equations, and those equations if we solve, we'll get this constant. So this is the approach we followed for constructing this shape function. Let us follow this approach and try to construct shape function for 6-node triangular element. Let's start. So we start with an approximation. This is the polynomial approximation, complete quadratic approximation. There are 6 constants to be determined. Now we impose the interpolation condition, and the interpolation condition is these equation approximation need to be satisfied at every node. So when it is satisfied at every node, evaluated at every node, this should give the nodal value. So this is the nodal value at node number 1. x1, y1 are the coordinates of node number 1. Now, so this condition needs to be satisfied at all the nodes. When you satisfied at all the nodes, we have this set of equations. So we have set 6 independent equations. There are 6 constants to be determined. We solve them and get the constants. So this is the equation we can write in a matrix form, and this will give us, these are the constants need to be evaluated, and u1, u2, u3, u4, these are the nodal values. So we have followed this approach while constructing shape function for a 3-node triangular element, and in that case our size of the matrix was 3 by 3. We had only 3 equations. But now we have 6 equations for 6 node triangle. It is just one scale in terms of the order of approximation. It is just one next level approximation. Now if you can go to even high level approximation, for instance, if we take cubic approximation or fourth order approximation, then you can think of what would be the size of this matrix, and evaluating that, solving these equations for every element, it's a very, very tedious job. It's algebraically very tedious job. For 3 node element, it is fine because our equations are only 3, but when we have equations more than 3, 6 and then we have 10, this is very tedious job. So we need to find out an alternative technique. Now, before we straight away go to the alternative technique, let us understand the technique, or let us develop the technique based on the understanding we already have for 3 node triangle. Okay, let's do that. So we know, if you recall, this is the shape function written in a very compact form for a 3 node triangle. Okay, now if you take any point, say point P, whose coordinate is xy, then the shape function evaluated at that point is this, and where alpha I, beta I and gamma I are the constants, and this depends on which node we want to evaluate. So alpha I is this, beta I is this, and gamma I is this, and for this I should not be equal to j and j should not be equal to k, and I, j, k permute in natural order means that it should be like this: 1, 2, 3, or 2, 3, 1, or 3, 1, 2, like this. So this is, if it is 1, 2, 3, means either it is 1, 2, 3, or 2, 3, 1, or 3, 1, 2, like this. This is the natural order. Now, so if we just write the shape function for node number 1, the node number 1 shape function will be this. Okay. Now, if we substitute all these values in this expression, our expression will be this. So we know this. Now, so let us write this equation in a slightly different form. This equation can be written like this. So this is essentially this, but written in a slightly different form. Now, think of an area like this. Consider an area A1, which is obtained by joining xy is the point we have within the element, and at that point we want to evaluate the shape function, and then A1 is the area by this point P, then node number 2 and node number 3. Now what should be then we know the coordinates of all the vertices. So this is one vertex and the vertex, and this coordinate is xy. This is another vertex, coordinate is x2, y2, and this is another vertex, coordinate is x3, y3. And we know, if we know the vertices of all the vertices, then this is how the area of a triangle can be evaluated. Okay. Now, so just compare these two. If we compare these two, then phi 1 can be written as this, and then this is the area we have just now checked, area A1. Area A1. So this can be written as, the phi 1 can be written as A1 by A, right? And what is A is the area of the triangle, and A1 is the triangle which is obtained by these 3 vertices, the point P within the element and node number 2 and node number 3. That gives you A1. Now similarly, if we take an area, say A2, which is obtained by the point P and then node number 1 and node number 3, and then we can show that phi 2 is equal to A2 by A1. And then if we take another area A3, which is again by point P and node number 1 and node number 2, we get phi 3 is equal to A3 by A. And for this, in order to get this, we have not done anything additional. Whatever we have discussed in one of the weeks, and this is the same thing, but we have seen that the shape functions can be represented in terms of the areas. Okay. Now, so let us, since the shape function is written, represented in terms of area, let us use a different symbol for that. Instead of phi 1, phi 2, phi 3, let us take L1, L2 and L3. And these L1, L2, L3 are called the area coordinates. We will have more discussion, detailed discussion on the area coordinates. Now, so at least by we can now visualize what is L1, L2, L3 based on the understanding of three-node triangular element we have. Okay. Now, let's then write this represent this area coordinate again in a different way, or the interpretation of the area coordinate in a different way. Suppose consider only node number 1. Let us try to understand only L1. Okay. Now, before we do that, there is another interesting point. So, let us take what is L1 plus L2 plus L3, L2 plus L3. L1 plus L2 plus L3 will be A1 plus A2 plus A3 divided by A, which is A divided by A means 1. Okay. And this is again not a surprise, because L1, L2, L3 are essentially phi 1, phi 2, phi 3, and phi 1, phi 2, phi 3 shape function must satisfy the partition of unity property, and this is partition of unity property, right? Now, let us have a different interpretation of this area coordinate. Now, only consider for node number 1, means shape functions or the area coordinate associated with node number 1, means L1. Suppose this is B, and this with these 2, 3 as a base, height of this triangle is h. Okay. Now, and then consider the coordinate of this point P in this direction, in normal direction, normal to the base direction is S. So, then we can write that A1 by A is equal to this. So, this is the total area and this is the area of A. This is the area of A1. So, this gives you S by H. Okay. So, it means that L1 can be written in terms of S by H. Okay. So, now for node number, on this line, if you take on this line we have S is equal to 0, because from there it is starting the coordinate S. S is a dimensionless parameter now. So, S will be 0, we are talking about only L1, please note, and this is how the S is defined for L1. Similarly, similar definition of S we can also have for other area coordinates as well, L2 and L3 as well, we will see that. But this is the picture that you can see on your screen now, it is for L1. So, L1 is 0, L1 is essentially phi 1, and L1 has to be 0 on this line on 2, 3, because this is the interpolation property. L1 will be 1 at node number 1, and other nodes it will be 0. So, on this line S will be 0, and substitute S is equal to 0, we have L1 is equal to 0. Now, on this line, this distance is S, so L1 will be S by H. Okay. And on this line, at node number 1, L1 will be 1, S is equal to H, so L1 will be 1. Okay. Now, so this is for a 3-node triangle. Now, let us extend the same philosophy for higher order triangular elements. For instance, for a 6-node triangular element, let us do it for L1. So, we have this, there L1 has to be 0, and then L1 will be 1. This we know. Now, for 6-noded triangle, this node number 4 is at the middle point of node number 1 and 2. Okay. So, if it is so, then in this direction S will be H by 2, and therefore L1 will be 0.5 here. And then what is the direction of L1? The direction of L1 will be this. Means in this direction we are moving. This is normal to line 2, 3. Okay. Now, similarly, similar thing we can have for L2 as well. So, L2 will be here it is it will be starting from this line. So, here L2 will be 0, at node number 2 L2 will be 1, and in the middle node L2 will be 0.5. Okay. Now, similarly, we can have L3 is equal to 1, L3 is equal to 0.5 here, and L3 is equal to 0. Okay. Now, so let us now represent the same thing, not in terms of L, in terms of S. Okay. Now, please note, when we write L2 is equal to 1, L2 is equal to 0.5, here we have just extended the idea of a 3-node triangular element. We have not claimed yet that these L2, L2, L1 are the shape function for 6-node triangle. No, we have not done that. We have just extended the idea of area coordinate in in higher order triangular element. But how to write the shape functions for higher order triangular element, we will come to that point shortly. Now, so let us represent the same thing in terms of this non-dimensional dimensionless parameter S. So for now S for triangular element, we have seen if for shape function 1 associated with node number 1, S is equal to 0 here and S will be is equal to 1 here, and the direction of S will be this. The same thing for higher order triangular element as well. So S will be is equal to 0 here, S will be 1 here, and S will be half here. This is for node number 1. And similarly, we can have for say 10-noded triangular element, where we are only talking about the shape function associate area coordinate for shape function associated to node number 1. Okay. So this is in this direction. On this line, S is equal to 0. Then on this line, S will be equal to 1, and on this line, S is equal to 1/3, because these two, these are all equal. This is very important. These nodes are equally spaced. Means on this triangular element, 6-noded triangular element, on one side we have just 2 nodes. We have 3 nodes, and these 3 nodes are equally spaced. Okay. Similarly, for this element we have total 4 nodes, and then distance of these 2 nodes are equal. So this is 2 nodes per side and equally spaced, and the order of the first one is linear, and total number of nodes will be 2 plus 1. This is equal to 3. Okay. Now, so second one, it is 3 nodes per side. All the nodes are equally spaced, and the approximation will be quadratic, and total number node will be 6. Means 3 and then 2, then 1. Similarly, for say 4 node per sides, total number of node will be 10, and then approximation will be cubic, and then all these nodes are equally spaced. Okay. So if your node number is, there are 2 nodes, then the degree of polynomial will be linear, means 2 minus 1, 1. If you have 3 nodes, then 3 minus 1 is equal to 2. Our approximation is quadratic. Degree of polynomial will be, the maximum degree will be 2, and then there are 4 nodes on one side. 4 minus 1, 1, 4 minus 1, 3. The degree of polynomial, the maximum degree will be 3, is a cubic polynomial. So now similarly, if we take a very general triangular element, higher order triangular elements, okay, these break line shows that these elements are means this, there are several other nodes between these and these nodes. There are several other nodes between these and these nodes. There are several other nodes between these and these nodes. Okay. Now, so for a higher order triangle with k nodes, all are equally spaced, then just now we have seen our total number of nodes in the element will be here the edge, it will be k, then k minus 1, then k minus 2, and so on, and finally 1. So this will be k into k plus 1 divided by, this will be the total number of node in a triangular element having k nodes per sides, equally spaced nodes. Okay. Now, then what will be the approximation order? The degree of polynomial will be k minus 1. Just now we have seen. Okay. Now, let us understand the shape function for just node number 1, 2, 3, or just node number 1, and then we will write a general expression. Okay. So what we have now, see on this line, L3 will be 0, right? On this line, L3 will be 0. L3 will be 1 similarly on this line. Similarly, on this line, L2 will be 0. And on this line, L1 will be 0. And L1 will be 1 on this line. Okay. And L2 will be 1 on this line. Okay. Now, this we know, right? Next is, suppose this is, so if it is k nodes we have per sides, and then total number of division will be k minus 1. So suppose this, at this point, this is S0, which is equal to 0. And then we have, at this point, we have say S1, and then similarly for some nodes we have say it is SP, say pth point, this is 0th point, this is first point, second point, it is pth point, and similarly finally it will be S k minus 1. K points, so it will be k minus 1, we have started from 0. Okay, this will be k minus 1. Now we know that k minus 1 will be equal to, it will be 1. So here it is starting from S is equal to 0, at this point k minus 1 will be 0. Now then for any arbitrary point along this edge, say point is pth point along this edge whose coordinate is SP, then we can write that this SP will be P divided by k minus 1, right? This we know. So we know what is the coordinates of the S coordinate of every point along the edge, along this direction. So this is the direction we are moving. So we know all the points on this line. We know S coordinate of all the points in this line. We know S coordinate of all the points in this line, this line, and then finally this line. Okay. Now we have to construct the shape function. Now shape function, when we construct the shape function, the points that we have taken, this is directly from the Pascal's triangle. So our approximation will be complete anyway, we have seen it. Then two things need to be satisfied. One is the interpolation property and the partition of unity property, right? Now, partition of unity property, at least for triangular element, we have seen the area coordinate, how it's satisfied. Now, interpolation property needs to be invoked when we construct the shape function. And what interpolation property tells us? Interpolation property tells us that if we have to construct shape function for 1, for instance, then suppose we have to construct shape function for node number 1, say phi 1. Say phi 1 we have to construct. And what are the property phi 1 must satisfy? Phi 1 must be equal to 1 at this point, and phi 1 must be equal to 0 at all other points. So what conditions we have? So phi 1 should be equal to 1 at sk minus 1, right? Or at L1, this is equal to L1, right? This is equal to L1 at xk minus 1, and phi 1 must be equal to 0 at all other points. And what are the points we have? We have, say, at L1 or S is equal to L1 is equal to 0 at this point. All these nodes here, all this node on this line, phi 1 must be 0. On all this node on this line, phi 1 must be 0. This, what would be the S1? S1 will be 1 by k minus 1. Phi 1 must be 0 at all this line, means it will be 2 by k minus 1, and finally it will be p by k minus 1, where p is equal to 0, then 1, and then 2 k minus 2. But only at sk minus 1, means which is at this point, phi 1 will be equal to 1. So that is the interpolation property. If you recall the serendipity, we actually tried to construct the shape function for a serendipity element involving these similar kind of interpolation property. Now, so next what we do is, this can be obtained. So these are the conditions we have. Now this can be obtained, these conditions can be satisfied by taking your shape functions like this. So L1 is the coordinate in this direction. Please note L1 is the coordinate in this direction. Okay. So at this point your L1, at this point L1 will be S0, at this point L1 will be here L1, at this point L1 is equal to S0, here L1 is equal to S1, and here L1 is equal to Sk minus 1. Okay. And some point P, here L1 is equal to Sp. Okay. So except for this node, all other nodes L phi 1 should be equal to 0. Now let us have an expression like this and then see whether these two conditions are satisfied or not. So these conditions, if we substitute any L1, if you take any node where the coordinates will be either S0, S1, S2, this will be 0 because the numerator part will be 0, right? And for S L1 is equal to K minus, this is L1 is equal to K minus 1, you will check that this will get cancelled, and if you substitute L1 is equal to K minus 1, this gets cancelled, and eventually entire thing will be 1. So the denominator and numerator will become same for L1 is equal to 1. So this gives us L1 is equal to 1 phi 1 is equal to 1 at L1 is equal to Sk minus 1 and 0 for at all other nodes. And that is the interpolation property we want, right? Now if we summarize, if we just write the entire thing in a compact notation, then for any, this is we have written just for node number 1, but if you write the similar thing for any arbitrary node within the element, this can be written like this: phi I is in any element, any node number within the element, phi I will be this, where fj and fji are defined like this. So fj are the functions of L1, L2, L3, and fji is the value of fj at node number I. Okay, at least from it, in order to understand this or for a better comprehension, we'll take one example and then see for different nodes how to consider it. We'll take say 6 node triangular elements or 10 node triangular elements and then check and find out the shape function for all the nodes using this expression, and there probably all these definitions of fj and fji will be clear, right? So let us stop here today. Next class we'll take one example, we'll take one triangular element and then see how using this concept the shape functions for triangular element can be constructed. Okay, then see you in the next class. Thank you.